Page 762, lesson 12.6 is on permutations and combinations. So kind of what we're looking at in this section is like how many different options there are of something happening. So just for example, so we make sure we know what we're talking about as we go through, they're talking about possible orders for watching 3 movies: comedy, drama, and action film. This first thing that they're showing on the left here, this is an example of a tree diagram. So a tree diagram kind of branches off different directions. The book's doing this a little differently than what sometimes you might see this as. Kind of just depends on the situation. In this case, I guess in this case there's really not much option because we're only having 3 different movies. So once we've picked a comedy and a drama, we only have one option left, would be action. Sometimes with tree diagrams, for things like if you're talking about flipping a coin, you could have heads or tails, and then you could have heads or tails, and then you could have heads or tails. So those might still have a branch even on the last part. The one in your book, the example in your book, doesn't have a branch on the last part because it's just picking 3 things. So tree diagrams potentially could look a little different depending what you're doing. And then the second option, what they're showing on the right is just a list. They're just listing out the different options here. So that would be a list. Okay. Either way you do that, you can see that there's 6 possible orders for watching those movies. And we'll talk about in a minute a way we could have figured that more easily if they didn't ask us to draw a tree diagram or make a list. So this is an example of independent events. When one event doesn't affect the result of a second event, then they're independent events. And when we have independent events, we can find the number of outcomes using the multiplication counting principle. So on the next page, multiplication counting principle. Sometimes it's called the fundamental counting principle. I've seen it named different things on different books. Basically, it says if there are m ways to make the first selection and n ways to make the second selection, there are m times n ways to make the 2 selections. So for example, if you have 5 shirts and 8 pairs of shorts, the number of possible outfits, we could take 5 times 8, which is 40. Going back to that previous example would be a little bit different, but we could have looked at it as our first movie, second movie, and third movie. And we could have looked at the different options we had. So we had a comedy, a drama, and an action movie. So for our first movie, we would have 3 different options. Once we've watched one of the movies, we're going to assume we're not going to watch it again. So then that would give us 2 options for our second movie. And then assuming we don't watch either of those movies again, then that's only going to give us 1 option for our last movie. And then same idea, what we could do is multiply those together. 3 times 2 is 6, 6 times 1 is 6. And so that would be another way to figure out that there's 6 options on what order we could watch those movies. So if you look at problem 1, use the diagram below. How many ways are there to get from the first floor to the 3rd floor using only escalators? So what they're doing is looking at this and saying, well, to get from the 1st to the 2nd floor, we have 2 different escalators. And then to get from the second to the third floor, we have 3 different escalators. So 2 options and then 3 options. So 2 times 3 gives us 6 different options. This one, there's really not that many choices, so I mean it wouldn't take you that long otherwise to just say, oh, they could go up this one and then this one, or they could go up that same one and then this one, or they could go up that same one and then this one. That's 3, and then the same thing over with the other one. And you could figure out pretty quickly there also that there would be 6 options. Sometimes the numbers are bigger and it's not really convenient to just count them all out though. So that's where the multiplication counting principle or fundamental counting principle can make things easier for you. So if you look at the got it, number 1, a pizza shop offers 8 vegetable toppings and 6 meat toppings. How many different pizzas can you order with 1 meat topping and 1 vegetable topping? So when you do these problems, I like to draw blanks so I can keep track of what's happening here. So we have, they're picking 1 meat topping and 1 vegetable topping. And here it says there's 6 meat toppings, so we have 6 options for that. And 8 vegetable topping options. And if we multiply, would be 48 options altogether. And then part B says, is a tree diagram a convenient way to find the answer to part A? Not compared to this, right? If I'm going to draw a tree diagram of all those different ways, I have meat option number 1, or if we want to make up 6 different meat topping options and 8 different vegetable options. Otherwise we're looking at, like meat option number 1 going to veggie option number 1, veggie option number 2, number 3, number 4, and so on. And then you got to do that for all the other ones. Not really convenient compared to just 6 times 8 is 48. So the next thing we're going to look at is permutations. Permutation, I'm going to modify a little bit what the book said here. Permutation, it's like an arrangement of objects where order matters. If the order matters, it's called a permutation. So this actually goes back to, we did that movie example earlier in the lesson. That would be an example of a permutation because we're saying the order matters on what order we watch those movies in. So if you look at problem 2, how many different batting orders can you have with 9 players? So with this, you probably would want to start out by drawing 9 blanks. You draw 9 blanks, and then you can think about for each of those blanks how many options you have. So if you have 9 people, for your first spot in the lineup, the leadoff spot, you've got 9 choices for who can be that batter. If that you choose one person there, the next spot you have 8 options, and then 7 options, all the way down to 1. If you multiply that all out, that's 362,880 options for how you could put a batting order. And that's if you have 9 people. That's not even including if you have extra people besides that. So it's a lot of choices that a manager has for something like that. And obviously there's certain reasons why they have people maybe bat in certain spots in the order, but that's how many options there would be. So the got it 2, a swimming pool has 8 lanes. How many ways can 8 swimmers be assigned lanes for a race? So this is very similar. We have 8 lanes, so we could draw 8 blanks for this. So we would have 8 options for the first lane that we're assigning. Next lane would have 7, and then 6, and then 5, and then 4, and then 3, and then 2, and then 1. And if we multiply all those together, that's going to tell us how many different options there could be. Now understand, I've watched Olympics and things that I've seen that, you know, actually there's certain lanes that like the best times get for like that final heat or whatever. So it's not just totally random, but that's what they're acting like in this, which would be maybe for the initial round, that might be the case. So that would be 40,320 different options for how the lane assignments could be given. So this obviously would be a lot quicker than doing a tree diagram to list out all those 40,320 options. It's still a little bit of work though, so they came up with an easier way for us to do this. So another way we can do this, if we're doing something where we go all the way from a number all the way down to 1 and we're multiplying the numbers together, we can use what's called a factorial. So factorial, so for example, if we were doing 3 times 2 times 1, that would be the same as 3 factorial. Okay, this 3 with the exclamation point, that's read as 3 factorial. Okay, same idea here. 5 times 4 times 3 times 2 times 1, that would be 5 factorial. So there's a way that you can do that on your calculators. So in order to do that, what you would do first of all would be type the number in. So like say you were going to do 5 factorial, you would type in a 5, and then if you hit the math button, which is on the left side, third button down, and then arrow all the way over to PRB, which stands for probability, and then choice number 4 is the exclamation point. You hit enter, and then you'll see a 5 exclamation on your screen, and you hit enter, and then that should give you the answer, which would be 120. Okay, so again, laziness sometimes, maybe, I don't know, but there will be some times, especially if there's like, you know, 15 numbers or something, that's going to take a little bit to type all of that in. You have this other shortcut option. Make sure though it's got to be all the way from that number all the way down to 1 in order for you to use this factorial. The next thing that the book talks about is permutation notation. So what they're saying is if you have a certain number of objects and you're picking a certain number of those, this is how you can work this out. There's a simpler way of doing this. So like in their example, what they're saying is if you have 8 things and you're picking 2 of them, okay? And there might be ways, I think there's probably a way you can do this on your calculator. I really don't care because we can't always use calculators. And I think there's an easier way of doing this than what the book's doing. So if you have 8 things and you're picking 2 of them, what I would say is we're picking 2 things. I'm going to draw 2 blanks. If there's 8 things, I have 8 options for picking the first thing. After I've picked that one thing, if I don't pick that same thing again, for the next one, I have 7 options. And if you multiply 8 times 7, you get 56. Notice we get the same answer as the book. Also notice all the stuff the book has, they're doing all this factorial stuff. We could cancel all these like factors out and we would have left 8 times 7. So it works what the book's doing. To me, this is a simpler way, just drawing the blanks for how many things you're picking and then put in the blanks what it is you're picking and then just get your answer that way. If the numbers are really big, you're doing really big, you know, like you have 12 blanks or something like that, the book's way then might be quicker just because you're otherwise, if you don't go all the way down to 1, you're going to have to type in all those multiplications. But again, I think it's just less to remember for you guys, and I think it's still manageable. You know, we're not doing 1,000 problems or anything, so I think we'll be able to handle that. So problem 3 goes along with that. Band has 7 new songs and wants to put 5 of them on a demo CD. How many arrangements of 5 songs are possible? So we have 7 songs, we're picking 5 of them. Again, you can do what the book's doing there if you want to. The other option is we're picking 5 things out of 7 options. We could just draw some blanks here, and we could say for the first song we have 7 options, and then we would have 6 options, and then 5 options, and then 4 options, and then 3 options. Now notice we're not going all the way down to 1, so do not use the factorial if you do it this way, but if you multiply those numbers together, then you'll get the same answer that the book has, 2,520. So we're going to talk about a problem that's not in your book here. If you have 6 students that are running for 3 different student council positions, president, vice president, and treasurer, how many different ways can these 3 offices be filled? So we're picking 3 different positions. So if you're using blanks, you would have 3 blanks here. For the first position, we would have 6 options, 6 different students that could possibly fill that. Once the first person was chosen, then there's 5 options for the next position, and then there's 4 options for the following position. If you multiply those together, is 120. So seems like a lot more than what you might expect with only 6 students, 120 different options, but that's what it is. And again, you can do it the way the book's doing. Just again to mention though that you won't always necessarily have a calculator to work these out. So this would be my suggested method for working this. So the next thing we're going to talk about is combinations. So a combination is where the order doesn't matter. Order doesn't matter. So maybe for example, if you're ordering a pizza and you say you want a sausage mushroom pizza, or you say you want a mushroom sausage pizza, it's both going to be the same pizza, right? Because it's the same toppings. So that would be an example where the order doesn't matter. What the book's showing is you can do what they're doing. So like if you have in their example there's 8 things and you're picking 2 of them, you can use this formula kind of. 8 factorial divided by 2 factorial times 8 minus 2 factorial, and you can work that out. It actually works out though. Another way of doing it is working it out like a permutation, like we just did, and then if you divide by the number of blanks factorial, then that will give you the same thing. So in other words, we have 8 things. Well, if we're going all the way, we have 8 things and we're picking 2 of them. So 2 blanks, 8 options, and then 7 options. And then we have 2 blanks. If you divide by 2 factorial, you'll get 56 divided by 2, which is the same as 28. So it kind of seems weird. We can, we could look at basically what the book's doing. Everything from 6 down to 1 could all cancel out with what they did, and then we'd be left with 8 times 7 divided by 2 times 1. So I'm kind of just looking at it as, making it possibly easier for you guys to remember than remembering this formula that the book's doing. It's just like we did previously with permutations. It's just that we divide by the number of blanks factorial. Dividing by the number of blanks factorial, what that does is that gets rid of our overlaps, so that we're not counting, in that example, not counting sausage, mushroom, and mushroom sausage as two different things. We're eliminating those kind of repeated things that are really the same as each other, since we don't care about the order here. So if you look at problem 4, 20 people report for jury duty. How many different 12-person juries can be chosen? Okay, so this one, here's a case where the numbers are bigger, and so it technically would come out probably easier for you to work out the book's way. But again, without memorizing anything, we could still do this like we've done before. So we're picking a 12-person jury, so we would have to have 12 blanks. And then we could think about there's 20 people, so we have 20 options for the first person chosen, and then 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, and we'd be multiplying those all together. Now that would be if the order mattered. That would be if it would be a permutation. Technically, if you were the first person chosen, or the 5th person chosen, or the last person chosen, if you're with the same other people on this jury, it really doesn't matter which order you were chosen in. So this is a combination. So we're going to divide this. Remember, we were picking 12 people, so we're going to divide by 12 factorial. To be safe, if you were doing that in your calculator, you could put all that first part in parentheses. I think with how you're typing it in, it would do all the multiplication first, and then it would divide by the 12 factorial anyway. So I think you could get by without doing the parentheses, but it doesn't hurt to have them there also. And when you work that out, then you should get the same answer as that the book had, 125,970. So if you look at the guide at 4, and how many different ways can you choose 3 types of flowers for a bouquet from a selection of 15 types of flowers? So we're picking 3 flowers, so we could put 3 blanks. So we're going to have 15 options for the first flower that we pick, and then we're going to assume that we're not going to pick the same flower more than once here. So that gives us 14 options for the next flower that we pick, then 13 options for the third flower we pick. We would multiply those together, and if we do that and only that, that's a permutation. The deal is, though, if I'm picking these 3 flowers, whether it was the first, the second, or the third flower that I chose, if I pick them in a different order, they're still going to be the same bouquet. So this is a combination. So we're going to divide, and we would need to divide by 3 factorial. We had 3 blanks, so number of blanks factorial. We divide by 3 factorial. And if you want to, when you're doing these, if you want to multiply the numbers on top and then do the 3 factorial on the bottom and then divide it out, you can. Otherwise, like I said, you can just put that numerator in parentheses. You can type it all at once in your calculator and get your answer. So that would be 455. So 455 different options for bouquets. So if you look at the lesson check number 7, how many outfits can you make with 6 shirts and 4 pairs of pants? So this, we would have 2 blanks. We're picking a shirt and pants. So we have 6 shirt options, 4 pants options. Multiply, we've got 24 different outfits. If you look at number 8, would you use permutations or combinations to find the number of possible arrangements of 10 students in a line, and why? And this would be permutations, because the order matters. Okay, if you've ever been in a line of people that you're going to lunch, you know the order matters to you, whether you're first in line or last in line. Okay, so that would be a permutation. So this gives you an idea of how to work with permutations and combinations.